Observations of a world 120 light-years away, the exoplanet K2-18b, have recently yielded data that could hold profound implications for the search for life beyond Earth. Using the advanced capabilities of the James Webb Space Telescope, astronomers analyzed the composition of this distant planet's atmosphere, revealing chemistry that has generated considerable scientific excitement and speculation. K2-18b orbits a red dwarf star, significantly smaller and cooler than our Sun, and resides within its star's habitable zone, the orbital region where liquid water could potentially exist on a planetary surface. Previous data had already suggested the presence of water vapor in its atmosphere. What the new JWST observations, however, the most compelling and also the most cautious finding from the JWST data is the tentative identification of a molecule called dimethyl sulfide, or DMS. On our planet Earth, the vast majority of DMS found in the atmosphere is a product of biological activity, primarily produced by marine phytoplankton thriving in the oceans. While non-biological processes can produce DMS, models suggest that achieving the observed potential concentration of DMS in K2-18b's specific atmospheric conditions would be challenging without a biological source. This makes DMS a potential biosignature, a chemical indicator whose presence could be strongly suggestive of life. It is crucial to approach this finding with scientific rigor and caution. The detection of DMS on K2-18b is, at this stage, tentative. The signal is relatively weak and requires independent confirmation through further observations. Scientists are working diligently to rule out any possible non-biological explanations for its presence. Atmospheric chemistry in alien environments can be complex and full of surprises. Therefore, while the potential is revolutionary, this is not, by any scientific standard, definitive proof of extraterrestrial life. It is a strong, compelling candidate that necessitates rigorous follow-up studies. The search for life is not a single discovery, but a process of accumulating evidence and eliminating alternative explanations. This potential breakthrough on K2-18b stands as a testament to the rapid evolution of exoplanet science. For most of human history, planets orbiting other stars were purely theoretical. The first confirmed exoplanet around a main sequence star, 51 Pegasi b, was discovered less than 30 years ago in 1995. This initial discovery, made using the radial velocity method, detecting the star's wobble caused by the planet's gravity, opened the floodgates. The field truly exploded with the advent of space-based telescopes like the Kepler Space Telescope, launched in 2009. Kepler utilized the transit method, staring at a fixed patch of the sky for years, monitoring the brightness of thousands of stars simultaneously. When a planet passes in front of its star from our perspective, it causes a tiny temporary dip in the star's light, a transit. Kepler discovered thousands of exoplanets, revealing that planets are not rare curiosities, but are ubiquitous throughout our galaxy, and that smaller planets, including rocky ones and those in super-Earth mini-Neptune size, range like K2-18b, are particularly common. Following Kepler, missions like the Transiting Exoplanet Survey Satellite, TESS, continued the census, surveying stars across the entire sky. But discovering exoplanets is only the first step. The next challenge is assessment, learning about these distant worlds. From transit data, we can determine a planet's size. From radial velocity data, we can estimate its mass. Combining size and mass allows us to calculate density providing clues about whether a planet is rocky, gaseous, or a mix, like the ambiguous nature of K2-18b before atmospheric data. The orbital period tells us how quickly it orbits its star, which helps estimate its temperature based on the star's energy output. However, the most tantalizing information comes from studying a planet's atmosphere. When an exoplanet transits its star, some of the star's light passes through the planet's atmosphere. By observing which wavelengths of light are absorbed by the atmospheric gases using a technique called transmission spectroscopy, we can identify the chemical composition. This is where the James Webb Space Telescope excels. JWST's sensitivity in infrared light allows it to probe the atmospheres of smaller, cooler planets orbiting fainter stars, precisely the kind of planets most likely to reside in habitable zones and potentially harbor life. The detection of molecules like water, methane, carbon dioxide, and potentially DMS on K2-18b is a direct result of this capability. Our concept of the habitable zone, while a useful starting point, is also undergoing refinement. Planets orbiting red dwarf stars like K2-18b are particularly interesting because red dwarfs are the most common type of star in the galaxy. However, their habitable zones are much closer to the star, meaning planets within this zone might be tidally locked, with one side perpetually facing the star and the other in eternal darkness. This could lead to extreme temperature differences, though thick atmospheres or oceans might help distribute heat. Furthermore, red dwarfs are prone to powerful flares and radiation bursts, which could strip away atmospheres or bombard any potential life. K2-18b's thick atmosphere might offer some protection, but the environment is clearly different from Earth's. The broader strategy in the search for life involves identifying potentially habitable planets, then using powerful telescopes like JWST to search for biosignatures in their atmospheres. Finding oxygen alongside methane, for example, would be a strong indicator of life, as these gases quickly react and wouldn't persist in equilibrium without a constant source, likely biological. The potential DMS on K2-18b adds another intriguing molecule to the list of potential biosignatures we are actively searching for. Other star systems like TRAPPIST-1, with several Earth-sized planets in the habitable zone of a red dwarf, are also high-priority targets for similar atmospheric analysis. This cosmic exploration inevitably brings us back to profound philosophical questions, none more prominent than the Fermi Paradox. If the universe is so vast, with billions of potentially habitable planets, where is everybody? If life can arise relatively easily, as the potential findings on K2-18b might suggest, why haven't we detected any signs of advanced technological civilizations? There are numerous proposed resolutions to this paradox. Perhaps complex intelligent life is exceedingly rare, even if microbial life is common. There might be great filters, challenging steps in evolution, like the transition from simple to complex life, or the development of technology, or existential threats that prevent civilizations from lasting or expanding across the galaxy. Perhaps technological civilizations are common, but they don't communicate in ways we recognize, or they quickly destroy themselves, or they are deliberately hiding their presence. K2-18b and future discoveries of potential biosignatures on other exoplanets might offer a clue. If microbial life is widespread, indicated by common biosignatures like DMS, it could lend weight to the idea that simple life is common, but the path to complexity or technology is the rare bottleneck. Alternatively, perhaps our methods of detecting life are still primitive, and we are only beginning to scratch the surface of what is truly out there. The journey to answer whether we are alone is just beginning. Future telescopes, both in space and on the ground, will push our capabilities further, allowing us to study the atmospheres of smaller, potentially rocky planets in habitable zones. Concepts for future observatories include instruments specifically designed to search for a wide range of biosignatures. The potential findings on K2-18b Bioc underscore the necessity and excitement of this ongoing scientific quest. Regardless of whether K2-18b hosts life or if its intriguing chemistry has another explanation, such discoveries refine our techniques, challenge our assumptions, and remind us of the universe's boundless complexity and potential.